Welcome viewers. In this video we'll see the work done followed by potential and potential difference. First we'll see the work done. So work done is nothing but a charge is Q is kept at the electric field that will experience a force in the direction of electric field. If you place a charge in the electric field, what will happen? The force will be developed on the charge. By referring this diagram, here the charge is available. This plus minus is the electric field. This is nothing but a electric field. In that electric field, charge is placed. So due to this electric field on the charge, the force is created. Force is developed. That is called F. On opposite side, we are having applied force, Fa. Force is applied on the opposite side. Electric field is available. Charge is placed. Due to electric field, this charge experiences a force that is nothing but F. On opposite side, we are applying one more force, Fa. If both are equal, then the charge will be remain in the same place. Suppose if Fa is greater than F, what will happen? The charge will move from this point A to point B. Right? If Fa applied force is greater than the force developed, mean the charge will move from the point A to point B. So what is the force applied and what is the distance moved is nothing but a work done. Right? Fa dot dl. So this description is given. F is the force experienced by the charge Q. Fa is the force applied on the opposite direction. If magnitude of Fa is equal to F, they remain same place, equilibrium. If Fa is slightly greater, then the charge will move from A to B. So the small work done by moving the charge is nothing but Fa dot dl. Very simple. So we are applying the force Fa. The charge is moving from one place to another place. That is called dl. So Fa dot dl is nothing but the work done by the charge. Fa dot dl. Right? So the total work done in moving a charge from A to B can be obtained by line integration. So this is due to only small length. The total work done can be obtained by the integrating on both the sides. We will get the total work done. So work done equal to integral A to B Fa dot dl. Right? A to B is the 2 points. In between A and B only the charge is moving. This is the applied force into dl. But F and this Fa is equal and opposite to the force developed. That is Fa equal to minus F. So that we can replace this Fa as minus F. Right? Now this is the applied force. Now it is replaced with the force developed. Fa and F are equal but in opposite, negative. So that minus Fa dot dl. But E equal to F by Q. Electric field intensity equal to force divided by charge. So cross multiply this. Force equal to electric field into charge. F equal to EQ. So that we can replace this F as E into Q dot dl. Right? Now the force is replaced with electric field intensity and charge from this relation. So finally what we got? Work done equal to minus. You bring this Q outside. It is a constant. Minus Q integral A to B E dot dl. So the general expression for the work done is nothing but minus Q integral A to B E dot dl. Right? Now we'll see the potential, electric potential. What is the definition for electric potential? Is also called as absolute potential. Is defined as the work done in moving a unit positive charge. Right? Work done in moving a unit positive charge from infinite to the field point. Absolute means it is from infinite to the field point. We are going to move the charges, positive charge, from infinite point to the field point. Right? So the work done in moving a unit positive charge from infinite to the field point. Now we'll first write the work done. What is work done? Just now we discussed minus q integral a to b e dot dl. Work done is nothing but minus q integral a to b e dot dl. Right? Now bring this charge in the denominator. So that work done divided by charge equal to minus integral a to b e dot dl. Right? Work done by charge. What is the work done by the charge? From the definition it is clearly given. Work done in moving a unit positive charge. So work done by charge is nothing but potential V. Right? So the potential V is nothing but work done by charge. So that is equal to minus integral a to b e dot dl. Right? Work done by charge is potential. Work done in moving a unit positive charge. So that this can be replaced as potential. Now we will replace this E as q divided by 4 pi epsilon x square into dx. Right? With a limit of a to b. Q, it is a general formula. Q divided by 4 pi epsilon x square into dx. Here we are having x, so here also dx. So this minus q divided by 4 pi epsilon is constant. Only we have integral a to b 1 by x square into dx. These terms are constant. So minus q divided by 4 pi epsilon integral 1 divided by x square is nothing but minus 1 by x. That you know that it is minus 1 by x. And what is the limit for this? It is nothing but work done in moving a unit charge from infinite to the field point. One is infinite, another one is the field point. So the limit is infinite and another point is r. Right? It is clearly given in the definition, infinite to the field point. Now we'll substitute the limit minus q divided by 4 pi epsilon. Here minus is there, minus 1 by r. Here 1 minus, in the lower limit 1 minus will be there, so it becomes plus 1 by infinite. So it becomes 0. Here 1 minus is available, here also 1 minus available. So q divided by 4 pi epsilon r. So the electric potential, the general formula is q divided by 4 pi epsilon r. Now we'll see the potential difference. What is potential difference? It is defined as the work done in moving a unit positive charge from point B to point A. Absolute potential means infinite to the point, field point, from infinite. But here potential difference is there. That means difference between 2 points, point B to point A. Same thing, work done in moving a unit positive charge, but it is from point B to point A. Right? It is clearly given. So potential difference VAB. Right? VAB refers means the potential difference between A and B equal to integral a to b e dot dl. Normally b to a, one negative will be there, that is replaced by exchanging the limit a to b e dot dl. Right? So directly we have got this expression. Now replace this E as q divided by 4 pi epsilon r square into dr. Here we are having r, so that it is given as dr. Right. Now this q divided by 4 pi epsilon is constant. Only we have integral a to b 1 by r square into dr. Right. Other terms are constant. So q divided by 4 pi epsilon, the integral 1 by r square is minus 1 by r. Now what is the limit? RA to RB, because point A to point B, that is clearly given. So that we are taking RA, RB. Now substitute the limit q divided by 4 pi epsilon minus 1 by RB plus 1 by RA. Right? So minus is there. While substituting the lower limit, it becomes plus. So we will rewrite this. So that q divided by 4 pi epsilon into 1 divided by RA minus 1 divided by RB. That is the potential difference between the 2 points A and B. The points are represented as RA, RB. Welcome viewers. In this video, we will see the relation between electric potential and electric field intensity. electric potential V and electric field intensity E, followed by some problems. First we'll see the relation between E and V, electric field intensity and potential V. Let us consider this diagram. So the point charge is placed at the origin. So charge Q is placed at the origin. The point P is located at a distance r meter. Here one point P is located at a distance r meter. This is the unit vector. AR is the unit vector. So this is the electric field intensity. Due to the charge at point P, the electric field intensity is created. Right? So the charge is placed at the origin. Point P is located at a distance r meter. AR is the unit vector. E is the electric field intensity at point P due to the charge Q. I will see the formula for this. So E equal to Q divided by 4 pi epsilon r square into AR cap. Electric field intensity is a general formula. Q divided by 4 pi epsilon r square. But we know that the del of 1 by r equal to minus 1 by r square into AR. The del operator. What is the del operator? It is a partial differentiation. Dou by dou x, dou by dou y, or dou by dou z. In case of r, it is dou by dou r, dou by dou pi, dou by dou theta, like that. Here only r is there. So by differentiating 1 by r is nothing but minus 1 by r square. So in this 1 by r square available here can be replaced by del of 1 by r. Okay. So from this relation, what we got? Del 1 by r equal to minus 1 by r square. See this in this expression E, Q divided by 4 pi epsilon r square. So 1 by r square. This 1 by r square is replaced by this value, del of 1 by r with negative. So that is given here. Q divided by 4 pi epsilon, right? 1 divided by this 1 by r square, now replaced by del of 1 by r. So by simplifying, we can write minus del Q divided by 4 pi epsilon r. What is Q divided by 4 pi epsilon r? That is nothing but potential V. Right? So now we can replace this as a V. So that E equal to minus del V. So finally what we got? Electric field intensity equal to minus del V. What is the meaning for this? The electric field is a negative potential gradient. Electric field and potential are negative gradient. This equation indicates the direction of electric field is opposite to the direction of rise of potential. Right? Both are negative gradient. The rise in electric field intensity is opposite to the rise of potential. E equal to minus del V. So by using this relation, we'll see a few problems. We'll see the first problem. The first problem is determine the electric field intensity. We need to find the electric field intensity E and unit vector for the point at a point 1, 1, minus 1. In the field of potential is given by V equal to 2x square y cube z. So in this problem, we need to find electric field intensity and unit vector. The potential is given. The potential equation is given 2x square y cube z, and point also given 1, 1, minus 1. So from V we need to find the E value, expression for E. So we know that the relation is available, E equal to minus del V. So by using this relation, we can find the electric field intensity from potential. What is del V? The V is nothing but 2x square y cube z. The value of V is given in the problem. What is del operator? I already told is a partial differentiation. Dou by dou x into ax vector, dou by dou y into ay vector, plus dou by dou z az vector. Partial differentiation with x, y and z. Now multiply this value, dou by dou x of 2x square y cube z into ax vector, dou by dou y of 2x square y cube z into ay vector, and dou by dou z of
2x square y cube z into az vector. So what is the meaning? This one we need to differentiate with respect to x. That is remaining terms are constant. Y and z are constant. What is the meaning of dou by dou y? We have to differentiate with respect to y. X and z is constant. Dou by dou z means we need to differentiate with respect to z. X and y are constant. Right? So while differentiating, what we are getting? Dou by dou s. So the x square. Differentiation of x square is 2x. Already one 2 is there, so that it is 4x y cube z. Right? This y cube z is written as it is. X square is the differentiation of x square is 2x. Already one 2 is there, so it becomes 4x. Then this one differentiation with respect to y. Right? So differentiation with respect to y cube. Differentiation of y cube is 3y square. Differentiation of y cube is 3y square. 3, already here 2 is there. 2 into 3, 6. 6x square y square z into ay vector. Right. Then differentiation with respect to z. Here z is available. So differentiation of z is 1. So only we have 2x square y cube into az vector. Right. So here we are differentiated with respect to x. That is 2x means x square means 2x. Y cube means 3y square. Z means 1. Now we got the relation. Now we got the expression for E. Now the point is given 1 comma 1 comma minus 1. So that we can substitute this point, so that we'll get the unit vector. E at 1 comma 1 comma minus 1. That is, we need to substitute x as 1, y equal to 1 and z equal to minus 1. Right? So 4 into x is 1. Then y cube, 1 cube. Z is minus 1 into ax. Similarly, 6 x square is 1. Y square 1. Z minus 1. Into 2 into x square y cube. Here z is not available. Right? Only here and here z is available. Here z is not available. So that due to negative, what we are getting? Already one negative available outside. Minus 4x minus 6ay. Here there is no negative, so it is plus 2az. Right? So minus of minus 4ax minus 6ay plus 2az. Now multiply this negative inside. So these two become positive. 4ax vector plus 6ay vector minus 2az vector. Because of positive, it becomes negative. What is unit vector? Unit vector is nothing but vector by scalar. The formula for unit vector is r vector by r, modulus of r. So the r vector is 4ax vector plus 6ay vector minus 2az vector. What is the magnitude? Square root of this? All these terms should be squared. 4 square plus 6 square plus minus 2 square. So that is equal to 56. So the unit vector will be 4ax vector plus 6ay vector minus 2az vector divided by square root of 56. So this is the unit vector. So this is nothing but electric field intensity. We calculated from the potential. This is the first answer, electric field intensity. After substituting the point, we got unit vector, this value. So in the second problem, we'll see that two identical spherical charges are available. Conducting sphere having a charges of 2 into 10 to the power minus 9 coulomb and minus 0.5 into 10 to the power minus 9 coulomb. Two charges in a spherical form is available. One value is 2 into 10 to the power minus 9 coulomb. Another is 0.5 into 10 to the power minus 9 coulomb. It is placed at a distance 4 centimeter. We need to find what is the force between them if they are brought into contact and separated by 4 centimeter. Right? Both are brought into contact, mixed together. Again it is separated by 4 centimeter. In both the cases, we need to find what is the force between them. Before brought into contact, after brought into contact, what is the force between them. That is the question, right? So this is a q1 value, this is a q2 value. The distance between is 4 centimeter, right? So the given data, this is q1, q2 and r value. So before brought into contact, first we will find the value, the two charges before brought into contact. So we can take this value as it is. Q1 is 2 into 10 to the power minus 7. Q2 is 0.5 minus 0.5 into 10 to the power minus 7. Right? The formula is 9 into 10 to the power 9. It's a scalar, not a vector. 9 into 10 to the power 9. Q1, Q2 divided by r square. So 9 into 10 to the power 9 is Q1 value. 2 into 10 to the power minus 9. Q2 value minus 0.5 into 10 to the power minus 9 divided by 4 centimeter. So that it is 4 into 10 to the power minus 2, converting into meter. So what we got? Minus 5.625 into 10 to the power minus 6 Newton. So before brought into contact, as a normal condition, these two charges as it is, by using this value we calculated the forces minus 5.625 into 10 to the power minus 6 Newton. Right. Now the charges are brought into contact. Both are added together. Q equal to Q1 plus Q2. We added both the charges. So 2 into 10 to the power minus 9 minus 0.5 into 10 to the power minus 9. So what is the value? 2 here, here minus 0.5 there. So it is 1.5 into 10 to the power minus 9 Coulomb. So while adding both the charges, what we got? 1.9 into 10 to the power minus 9 Coulomb. Now again it is separated, brought into contact. Again it is separated into two parts. That also placed at 4 centimeter. What will happen if it is separated? The charges will be splitted into two equal parts. That is the important thing. This is the one value 2. Another charge is minus 0.5. Both are added together. What we got? 1.5. But while splitting, the nature of the charge is it will split into two equal parts. Right? That is the one nature, one property of the charge. Charge will be splitted into two equal parts. So that Q1 and Q2 equal to half of this value. 1.5 is 1.5 into 10 to the power minus 2 divided by 2 means 0.75 into 10 to the power minus 9 Coulomb. It is splitted into exactly half. 0.75 minus 9 into 10 to the power minus 9 Coulomb. Now both Q1 Q2 are same value. So by using this value we can find the force again. Right? The same formula, 9 into 10 to the power 9, this is Q1 and Q2, both are equal, divided by the distance. So what we got? 3.164 into 10 to the power minus 6 Newton. Right? So the first condition what we calculated without normal case, without brought into contact. After brought into contact, both are mixed together. The important point is while splitting, it will split into two equal parts. Exactly half of the charge will be splitted, right? So the 1.5 means while splitting into 2, it will be 0.75 into 10 to the power minus 9 Coulomb. Both Q1 and Q2 will be same value, splitted into equal parts, right? By using this charge, we calculated the forces 3.164 into 10 to the power minus 6 Newton. Now we'll see the third problem. 3 equal positive charges. The value is 4 into 10 to the power minus 9. Each are located at 3 corners of the square of side 20 centimeter. Right? The one square is available with the side 20 centimeter. At the 3 corners, this 4 into 10 to the power minus 9 Coulomb charge is placed. All 3 corners are equal value. Now our question is determine the magnitude and direction of electric field at the back end corner of the square. The 3 corners, the charges are placed. One more corner is there. At that corner, we need to find what is the electric field intensity, magnitude as well as direction. So this is the given problem. We'll see the diagram. So this is a square with 20 centimeter. Right? R equal to 20 centimeter, that is 20 into 10 to the power minus 2, that is 0.2 meter. Right? It's a square with 0.2 meter, so 0.2 is given. these three corners the charges are placed. We will assume that Q1, Q2, Q3. These three corners the charges are placed. What is the value of the charge? 4 into 10 to the power minus 9 coulomb. The charge value is equal. All three corners having equal amount of charge. Our aim is the remaining corner is available. We need to find, the question is, we need to find the electric field intensity at the fourth corner due to this Q1, Q2 and Q3. Right? So that is nothing but we will take it as this E2. I will see one by one. So at this corner we need to find the electric field intensity. First consider Q1. So the electric field intensity due to Q1 will be E1 in this direction. Both are available in the same line. So only one component E1. Right? So the E1 is the electric field intensity on point P due to the charge Q1. Due to both are placed in the same line, only we have the E1, only horizontal component. Now consider Q3. Q3, due to Q3, the electric field intensity available in point P is E3. These two also available in the same line. So we have only one component, E3 is a vertical component. Right? So E1 is the electric field intensity due to Q1. E3 is the electric field intensity at point P due to Q3. So these are all available in the same line. But we'll consider in Q2, this corner, the electric field intensity is E2 at this point P, but it is available at an angle of 45 degree. It is located at an angle of 45 degree. But Q1 and Q2 placed at the same line. There is no horizontal or vertical component. But these two are, this point and this point is placed at a distance at an angle of 45 degree. So that this E2 is split into two components, vertical component and horizontal component, EV, EH. The sum of EV and EH equal to E2. Right? So now what are the components we have? E1 is available, E3 is available, EV is available, EH is available. This E1 and EH, these two are horizontal component. E3 and EV, these two are vertical components. Like that we can find, easily we can able to find. So we will find E1, E3, EV and EH. So by adding all, we will get the total electric field intensity at point P due to Q1, Q2 and Q3. Right? So first we will consider the charge Q1. It is very simple. E equal to Q divided by 4 pi epsilon r square. That is the formula. This is a unit vector. Right? Because the Q1 located in the same line. So there is no other component, only we have E1 only. So E1 equal to Q divided by 4 pi epsilon r square. Q is 4 into 10 to the power minus 9 divided by 4 into pi into epsilon naught is 8.854 into 10 to the power minus 12. It is, we consider as a air medium. So the epsilon r equal to 1. And r value is 0.2. This 0.2 is available. 0.2 square. So what we got? E1 equal to 900 AX, voltage per meter. Right? 900. So while considering Q1, the E1 value will be 900. Only one component. Now consider Q2. While considering Q2, what is the thing? We have horizontal component as well as vertical component. Horizontal component is in general total component multiplied by cos of theta. Vertical component equal to total component multiplied by sin of theta. Here theta is 45 degree. It's a general formula. Horizontal component equal to total component multiplied by cos 45. Vertical component equal to total component multiplied by sin 45. Now what is this r value? We need this r value. That is the important thing. From the diagram, see this, the distance between point P and Q1 is 0.2. Distance between point P and Q3 also 0.2. But distance between Q2 and point P is not known. We need to find from Pythagoras theorem, because these two values are known, 0.2, 0.2. So according to Pythagoras theorem, this value, let us consider r equal to square root of r square equal to 0.2 square plus 0.2 square. So we need this distance. This distance can be calculated using this Pythagoras theorem, right? R equal to square root of 0.2 square plus 0.2 square. So finally what we got? Square root of 0.08, that is nothing but 0.2828 meter, right? So what we need is, this distance is needed, that is 0.2828 meter, that is calculated from the Pythagoras theorem, right? Now we need to find what is the horizontal component and vertical component. Now we got the value of r. So while considering the second charge, E2 is the vector sum of horizontal component plus vertical component. Horizontal component is E2 cos 45 into AX vector plus E2 sin 45 into AY vector. This is horizontal component, this will be vertical component. You take the E2 outside, so we have cos 45 AX plus sin 45 AY. What is E? Q divided by 4 pi epsilon r square. So this r is already we calculated based on the Pythagoras theorem, into cos 45 AX plus sin 45 AY. Right. Now we'll substitute the value. The Q is 4 into 10 to the power minus 9. This cos 45 is 1 by root 2 into AX. Sin 45 also 1 by root 2 into AY. Now A in 4 into pi into epsilon is epsilon naught, 8.854 into 10 to the power minus 12 into r. R value we calculated 0.2828 square, right? So by simplifying this, what we got? 450. By multiplying inside, what we got? 320 AX plus 320 AY, right? So while considering the second charge, we have horizontal and vertical component. So that is given as 320 AX plus 320 AY, right? Now we'll go to the third charge. Third charge, again it is same, because there is the charge value and distance is already equal. So the E3 is equal to E1. E1 we already calculated 900 AX. So E3 also 900 AY. Only it is available as a vertical. So that no need to calculate again. The already calculated E1 value taken as E3. Both E1 and E3 are same. Only E1 is the horizontal component, E3 will be vertical component. Now we got all three values due to Q1, Q2, Q3. So that can be added together. So E equal to E1 plus E2 plus E3. So the E1 equal to 900 into AX, horizontal. E2 having two values, horizontal component and vertical component. Just now we calculated. And E3 900 AY. These two are equal. This is horizontal, this is vertical. Now we can add all, so that 1220 AX plus 1220 AY, right? So by taking the modulus, what we got? 1725.3 voltage per meter. So the electric field intensity at the fourth corner, due to the remaining three corners, Q1, Q2, Q3 will be this value, 1725.3 volt per meter.
Welcome viewers. In this video we'll see the coordinate system. In that there are three type of coordinate system available: Cartesian coordinate, spherical coordinate and cylindrical coordinate system. First we'll see the Cartesian coordinate system. It is also called as a rectangular coordinate system. So in this coordinate system, it is represented by x, y, z. What we are drawn the graph sheet. The data are drawn in the graph x and y axis. Here we have x, y and z, three-dimensional axis available. That is, all three are length. The three parameter what we are represented as x, y, z, that is nothing but a length, right? So we'll see the diagram. So the consider a point P, X, Y, Z in space at a distance r meter from the origin. So we have the three axes available: X axis, Y axis and Z axis, right? In order to represent this X, Y, Z, we consider one point P at a distance r meter from the origin. So this is nothing but X, Y and Z, representing three different points X, Y and Z. So corresponding this value will be Z into AZ, that is the unit vector in Z axis. The corresponding this value will be YAY, unit vector in Y axis. The corresponding this value will be XAX, that is nothing but unit vector in X axis. So this will be very similar to the graph what we are drawn, that is XY axis. Here we have X, Y and Z axis. All are measured in the terms of length. So this R vector can be represented as XAX plus YAY and ZAZ, right? This is not AY, is AZ. This AX, AY, AZ are the unit vectors. This XY, Z is the component vector. So in this entire Cartesian coordinate or rectangular coordinate, we are representing XY, Z. This corresponding AX, AY, AZ are the unit vectors. Right. Now we'll see how to represent the unit vector. You know that unit vector is nothing but vector by scalar. R vector divided by R. So the R vector is nothing but X AX plus Y AY plus Z AZ. So the scalar is represented as square root of X square plus Y square plus Z square. So this unit vector is represented as vector by scalar. In order to represent the differential length, area and volume, we consider a point P, X, Y, Z. That already we considered point P, X, Y, Z in the rectangular coordinate system. Now we are going to increase the coordinate system by differential element. That is, we are going to increase the X by X plus dx, Y by Y plus dy, Z is Z plus dz, right? It is incremented, it is increased by the differential element dx, dy and dz, so that we can go for calculate the differential area, volume and length, right? Now we already considered point xyz. Now it is increased into x plus dx, y plus dy and z plus dx, right? From this, so the differential length is now from point P to point Q. So point Q is the new one by increased by differential element, right? So based on that, the differential length dl is nothing but dx ax vector plus dy ay vector plus dz az vector, right? So these are all nothing but incremental element dx, dy and dz, right? While taking modulus, it is square root of dx square plus dy square plus dz square, that we know very well. From this vector we can calculate the modulus of dl. So this is the value, right? So this is a length. We consider x, y and z. So while calculating differential area, we need to consider any two element, either xy or yz or zx, right? So first we consider dsz. So here z is there, mean dx and dy. We consider x and y that represent z axis. So dsz is dx dy into az vector, unit vector. So dsx is dy dz into ax. dsy is dz dx into ay, right? We are multiplying two parameters, x and y and z and x, right? So that because of area we need to multiply only two elements. So while going with a differential volume means length, breadth and height. So we need to multiply all three elements, dx, dy and dz, right? So in this coordinate system we represented x, y, z normal length. Then we increased into dx, dy, dz. From that we calculated the differential length. then modulus of differential length and the area by multiplying two parameters, then volume multiplying three parameters, right? So this x, y, z all are length, represented as a length, right? Now we'll go to the second coordinate system, cylindrical coordinate system. Right? The cylindrical coordinate system represented by r, theta and z. It's not a r, it's a rho. Rho, pi and z. What is rho? Rho is the radius, that is the length. Pi is the angle, azimuthal angle. Z is the height, right? So in this cylindrical coordinate system, the two length available and one angle is available. In the previous system, all three are length parameters, right? Here we have two length available and one angle is available. If you want to represent any system with two length and one angle, we can use this cylindrical coordinate system. That's represented by rho, pi and z, right? So that we can represent the system with two length and one angle. Now we'll see the diagram. So this is x, y, z axis available. So this diagram is drawn as a cylindrical form. This is a point P. Is represented by three parameters. One is this angle, another one this length rho, another one this height z, right? So it is represented by one angle, one length rho and one height z, right? So we have rho, pi and z. It is represented by this. This point P is represented by these three parameters. Now in order to find the differential length, area and volume, we consider the differential volume element in the cylindrical coordinate system by increasing r pi z into dr, d pi, dz, right? In order to go for a differential volume, area and length, it is increased by the differential increment dr, d pi and dz, right? The volume element become very small. Its shape approaches that of rectangular parallelepiped and it has side the length of dr, r, d pi and dz, because dr and dz are already length, is a length component, but d pi is the angle. So in order to convert into length, it is multiplied by r into d pi. So r into d pi is equivalent to length. So this is also length, this is also length. Now pi also converted into length. D pi means angle, r d pi means equivalent length, right? Now we have three parameters, dr, r d pi and dz. From that we can easily calculate the differential length dl. Differential length is square root of dr square plus r d pi square plus dz square, right? So this is length and this is also equivalent to length. Angle is converted into length. So while going with the differential area, it is multiplied by two parameters, r dr into d pi, dr into dz, r d pi into dz. So we are multiplying two parameters. While going with the differential volume, we can multiply all these three parameters, dr, r d pi and dz. So while volume, we are represented multiplied all three parameters, right? So in this cylindrical coordinate system, we have two length and one angle, that is represented by length and differential area and volume. Now we'll go to the third system, spherical coordinate system. So in the spherical coordinate system, what are the things available? R, theta and pi. See, this r is the length, theta and pi is the angle. So one length is available and two angles available. So in the first system, all three are length. In the second system, two length and one angle. In the third system, one length and two angle. So any system, if you want to represent either length or angle, you can choose any one of these three, either one length or two length or one angle, two angle, according to our requirement, right? So this is a spherical coordinate system with radius and two angles, right? You'll see the diagram. Same thing, we have the x-axis, y-axis and z-axis. This point P is located in a spherical form. These lines are drawn in a spherical form. This point P is located, right? So that the distance is r. So we got one length. This angle will be theta. This angle where it is cuts here, this angle is pi, right? So the P is nothing but represented by r, theta and pi, right? One length and two angles. So this theta will vary from 0 to pi, 180 degree. But pi will vary from 0 to 2 pi, 360 degree. Entire 360 degree it will vary. In order to find the differential volume, now this r, theta and pi is increased into dr, d pi and d theta, right? So the dr is already length, but d pi and d theta are the angles. So that should be represented in the in terms of length. So that this d pi is nothing but r into d pi, r into d theta. R into d theta is equivalent to the length. Similarly, this d pi is converted into r sin theta into d pi. So this also now represented as a length. So this is also length, this is also length, this is also length, right? So we cannot go with a angle. So the angle is, the equivalent angle is converted into length. D theta is r d theta. D pi is r sin theta d pi. From these three parameters, we can easily calculate the differential length, volume and area. So differential length dl is dr square, square root of dr square plus r d theta square plus r sin theta d pi square, right? So we can find the differential length, right? All three now become a length parameters. The angles, these two angles are converted into length. While going with a differential area, it is multiplied with two parameters, r dr into d pi, r dr sin theta into d pi, or r d theta r sin theta d pi. Two elements are multiplied in order to get the area, differential area. While going with a differential volume, it is dr r d pi r d theta r sin theta d pi, right? So r available two times, r square sin theta d theta d pi and dr. So here multiplied all three parameters. So in the spherical coordinate system, it is represented by r, theta and pi. One angle with one length and two angles is given by these three parameters, right? So while comparing all these three, you can able to easily understand. So in the Cartesian coordinate or a rectangular coordinate, we have x, y, z. While going with the cylindrical coordinate, rho, pi and z. While going with the cylindrical, we have r, theta and pi. So these three parameters available. So the any system, according to our requirement, we can choose any one of these that will be fit to either length or two length with one angle, or one length with two angle can be selected. Now we'll see the transformation. We can convert the coordinate system from one coordinate system to another coordinate system. In order to go further simplification, further calculation or further representation, we can convert from one coordinate system to another coordinate system. First we will see the Cartesian coordinate system to cylindrical, right? Cartesian means you know that x, y, z. Suppose you are having x, y, z, three parameters are available. If you want to convert into cylindrical coordinate, that is rho, pi and z, that is possible. How will you convert this rho? Rho is nothing but square root of x square plus y square. See, by using these three parameters are represented. Right? Rho is represented as square root of x square plus y square. Pi is nothing but tan inverse y by x. Z is taken as it is. Right? So that from x, y, z Cartesian system, we can convert into cylindrical system by using this formula. Similarly, cylindrical to Cartesian, that is reversed. Cylindrical we are having rho, pi and z. From that we can convert x, y, z. How will we convert? X is nothing but rho cos pi. Y is nothing but rho sin pi. Z is taken as it is. Right? So that we are able to convert cylindrical system into Cartesian system. We can calculate this x, y, z by using this formula. Then another is Cartesian to spherical coordinate, that is x, y, z into r, theta and pi, right? This is a Cartesian, this is a spherical. How will you calculate r? So square root of x square plus y square plus z square. How will you calculate theta? Cos inverse z by r. How will you calculate pi? Tan inverse y by x, right? So this Cartesian can be converted into spherical by using this formula. Then spherical to Cartesian, again it is reversed. Spherical is available, r, theta, pi is available. We can convert into x, y, z, right? How will you find x? X equal to r sin theta cos pi, y equal to r sin theta sin pi, right? Z equal to r cos theta. So by using this formula, r, theta, pi can be converted into x, y, z, right? So for the further simplification and further calculation, we can convert from one coordinate system to another coordinate system also. Thus equivalent formulas are available.